In the last video, we took a look at friction in piping systems. And remember, that comes in two forms. There's minor losses, which is friction in fittings, and there's pipe friction, which is the friction in long, straight lengths of pipe. Now remember, what we were doing there is undoing one of the assumptions that we made when we came up with Bernoulli's equation. One of those assumptions was frictionless flow. Well, if we're going to apply Bernoulli's equation to piping systems, that's a terrible assumption. So we needed to bring that term back into Bernoulli's equation, and it was a pressure loss term. So what we're seeing here is the result of that modification to Bernoulli's equation to bring pressure losses back into the equation. So that's what the last couple videos was talking about, was how to calculate this pressure loss term. Well, this video is concerned with what happens with a piping system which has a pump in it. So in order to accommodate pumps in our piping systems, we need to go back and make another modification to Bernoulli's equation. Because if you go back and look, you'll see that one of the assumptions we made in coming up with Bernoulli's equation is no shaft work. Well, if there's a pump between point 1 and point 2 in our piping system, then there's definitely shaft work. So there's a work input to our system. So remember, Bernoulli's equation is an energy equation. So that work input needs to be accounted for in the energy balance. So for systems where we have a pump, we have to add an additional term to this equation called delta P pump, and that's the pressure increase over the pump. Now notice that there's a negative sign here, so we're subtracting this off of the right-hand side of the equation. Well, that's the proper sign for an energy input to our system, because remember, this point 2 is a downstream location. Remember that losses, frictional losses, are added to the right-hand side because the sum of these three terms is decreasing. So we need our pressure loss term to maintain the equality here. Well, by the same token, an energy input into the system would be subtracted from the right-hand side. So this is now Bernoulli's equation with losses and with a pump added in. Now, we'll be discussing a little bit later on in this video about exactly what this delta P pump looks like. How does it vary with different properties? For the purposes of this video, we're going to assume that that pressure increase is achieved by a centrifugal pump. Now, the last module in the course is on turbo machinery, and it's in that module where we'll take a close look at centrifugal pumps and understand exactly how they work. However, for the purposes of this video, we're going to be introducing some basic characteristics of a centrifugal pump a little bit later on. So we want to continue to work with this equation now. What I'm going to do is take this delta P pump term and move it over to the left-hand side all by itself, and move all of these things over to the right-hand side. So when we do that, we get our delta P pump term all by itself on the left-hand side. Remember, that's the pressure increase across the pump, but because this is an energy conservation equation, you want to think of that as the energy input or the work input due to the pump. Now, what I've done in these three terms is take the basic terms in Bernoulli's equation and show them as differences. So P2 minus P1, rho g, Z2 minus Z1, plus rho over 2, V2 squared minus V1 squared. So that's the three basic terms in Bernoulli's equation. Now, the other thing I've done here is expanded out the delta PL, or the pressure loss terms, just to remind us that that's made up of minor losses and pipe friction. And the last two videos looked into those two terms in detail. Well, arranged like this, the right-hand side of this equation is known as the system pressure. So the way you want to think of this is the pressure provided by the pump, and this is the pressure required by the system. So all of the different places that the pressure changes in a system. Now, it makes more sense if you think of it in terms of energy. This is the energy input of the pump, and this is all of the places that that energy goes. And of course, those two need to balance because this is an energy equation, conservation of energy equation. So the right-hand side altogether is called the system pressure. Now, we're going to break this down into two parts, and it's important to understand why it's broken down into two parts, and it's going to be an important feature of when we start connecting centrifugal pumps to piping systems. So the first two terms here are called the fixed system pressure, and the rest of the terms combined together are called the variable system pressure. So these are two very important terms in this section of the course. Now I want to make sure we understand what we mean by fixed and variable. If you take a look at these two terms, you say, well, why are we calling this fixed? These elevations could change. If we changed our piping system, changed the elevation of the exit or the inlet, this is certainly not fixed. Well, it's not fixed in that sense. The key thing to realize is that fixed and variable here is referring to the flow rate through the piping system. Okay, so the flow rate through the piping system. So realize that these two terms don't have a velocity in them, whereas all of these terms do have a velocity in them. Okay, so we have our kinetic energy term here certainly has velocity, and the pressure losses and the friction loss all have velocity in them. So everything in the variable system pressure depends on V, the velocity in the pipe, or in a moment we're going to convert that over to the flow rate through the pipe. So the words fixed and variable refer to the flow rate through the piping system. The first two terms are independent of the flow rate, so these energy requirements are independent of how much flow there actually is in the piping system, whereas all of these energy requirements depend on that flow rate. Now, in addition to these being dependent on flow rate, notice that all of these V's in here are squared. So the variable system pressure varies approximately as V squared. So our variable system pressures are approximately a function of V squared. Now realize that if they're a function of V squared, they're also a function of Q squared. And Q is our volume flow rate. So in thermodynamics, Q was heat transfer, but in this course, uppercase Q is a volume flow rate. So in SI units, this would be cubic meters per second. Now realize that if the variable system pressure are a function of V squared, they're also a function of Q squared. And that's the more usual way to write the variable system pressure, is as a function of the flow rate squared, not as a function of the velocity squared. So we'll be seeing that in a moment. Now, why here do we say approximately? Well, if we look at the kinetic energy term, it's definitely a function of V squared. There's nothing approximate about that, because remember, density is constant. Same thing with the minor loss term. It's definitely a function of V squared, because this K is a constant. But the pipe friction term, remember this friction factor is actually a function of two things. It's a function of pipe roughness, but it's also a function of Reynolds number. And remember, Reynolds number has the velocity in it. So this pipe friction term is not exactly proportional to V squared. Now it turns out it's actually still quite close to being proportional to V squared. So that's why here I say this is approximately a function of V squared, and therefore approximately a function of the volume flow rate squared. Remember the connection between V and Q. Q is equal to V times A, the cross-sectional area of the pipe. So if you know one of those, you know the other. What this allows us to do is write the system pressure in a more compact form. So delta P system, which remember is the entire right-hand side, is A, so that's our fixed system pressure, plus BQ squared. So B would be all of these coefficients out in front combined together in an appropriate way. Okay, so notice that system pressure curves, because we're going to start to plot these next, are going to be parabolas. They're going to be shifted up and down by an amount A, and how steeply they open up is going to be governed by that parameter B, but they're going to be parabolas. So let's go on to plot a system curve next. So a system curve, which is what we're seeing here, is a plot of this system pressure versus the volume flow rate through the piping system. And as we saw on the previous slide, that's going to be a parabola. So this particular parabola has a fixed system pressure equal to that amount, and its variable system pressure is the portion above this location here. So if we happen to be operating at this particular point, so the flow rate through that piping system is this value here, then this portion is the fixed system pressure, and from there up to here would be the variable system pressure. So the sum of those two giving the total system pressure, which is this quantity here. So that's what a system curve looks like. Now the next thing we want to do is figure out where on this system curve would we be operating, or what is the operating point. Well, let's go back to our equation just to see how this is going to work. What we've been talking about for the last little while here is the right-hand side of this equation, the system pressure. Well, let's remind ourselves that that actually needs to be equal to the pump pressure. So the system pressure equals the pump pressure. The pump pressure is the input of energy, and the system pressure is the places that all that energy is going. So what we want to do is introduce, what does a pump curve look like? In other words, if we go to these same axes, horizontal axis here is volume flow rate, and the vertical axis is delta P, what does a so-called pump curve look like? Well, for a centrifugal pump, a typical pump curve looks like this. And we'll go into this in great detail in the turbo machinery section of the course, but centrifugal pumps are capable of providing a certain pressure increase which decreases as the flow rate increases. Okay, so if you imagine you have a centrifugal pump and you've got a valve on its exit so you can control the flow through the pump, and you're measuring the pressure change across the pump, if you close that valve so there's only a tiny little bit of flow, or perhaps even no flow, you'll have a maximum pressure increase across that pump. As you open up that valve and allow more and more flow through, the flow will certainly increase, but what will happen is it tends to be a little bit flat here at the beginning, but what will eventually happen is the pressure increase across the pump will drop off. So this is a very typical pump curve, and a pump curve is a characteristic of every pump design that shows the pressure increase it provides as a function of the flow rate that it's providing. Okay, so delta P across the pump versus the flow rate through the pump. Well, that represents the characteristics of our centrifugal pump. Well, now we're going to take that centrifugal pump and hook it up to a piping system that we've been talking about. Well, the key thing here is that where those two curves cross is the operating point. Because remember, our equation says delta P pump, which is this line, has to equal delta P system, which is that line. Well, there's only one flow rate where that happens, and that's the operating point. So if we drop straight down from that point, the flow rate will be this value here. So if we take this particular pump, characterized by that pump curve, and we hook it up to this particular system, characterized by that system curve, and we ask ourselves, what's the flow rate going to be? Graphically, at least, the answer is that value right there. And if we're also interested in what is the pressure the pump is producing and what are the pressure requirements of our system, then that would be this value right here. Usually we're interested in the flow rate, but we may also be interested in the pressure being provided as well. Now the next thing we want to do is start to understand how changes in this operating point come about. In other words, we have a particular pump hooked up to a particular piping system. How do we change the flow rate? Well, there's two basic things that can happen to cause that flow rate to change. The first one is we could change something that is in the variable system pressure part of that equation. Let's say this piping system had a valve in it, and that valve was partially open. And we went and we opened the valve a little bit. Well, we would expect from common sense that the flow rate would increase, right? But let's think about what's happening in the equations. When we open a valve, we are reducing the minor loss coefficient associated with that valve. So if we go back to our system curve equation, there's a Km in there. One of those Km's is the valve that we're talking about. We open the valve, that value of Km decreases. So we're decreasing the variable system pressure, or we're decreasing the value of B. So what would happen is this parabola would not rise as quickly. So by decreasing that K value, by opening up the valve, our new system curve would perhaps look like that. So the operating point is moved from there to there, and so the flow rate has increased to this new value, and of course the pressure has decreased a little bit down to that new value. So this is how we could figure out what the new flow rate is after that valve has been opened more, or the Km value associated with the valve has decreased. If we happen to close the valve instead of opening it, well, we would just move the other way. So our new operating point would be here, and the flow rate would be decreased. So what we're doing when we adjust the valve position is we're changing the value of this B, because that minor loss coefficient associated with the valve that we've been talking about is buried inside of this B. And if you go back and look at the full system equation, you can see where that is. So changing B changes the steepness, I'll call it, of this parabola. Decreasing B makes it a shallower slope like this. Increasing B makes it a much higher slope and moves our operating point to the left. So that's what happens when we change the variable system pressure. Now if we take a look at the other possibility, and that's changing the fixed system pressure, if we change either of the two terms in the fixed system pressure, what we're doing is taking that system curve and shifting it vertically. So here I'll show what happens if we shift it downwards. Now in practice, what is one of the ways we could shift the fixed system pressure downwards? Well, if we have the exit of our pipes, Z2 at a particular elevation, 100 meters higher than Z1, let's say, and we were to move it downwards, then we're reducing our fixed system pressure. So we're shifting this whole parabola straight down, and we would see the flow rate would increase. If we were to do the opposite and shift our system curve upwards, then the flow rate would decrease. That would be our new operating point. So anything we do to change the fixed system pressure, we're again moving this parabola, but we're just shifting it up and down by changing this quantity here. So this is how pump curves and system curves combine together to show us where the operating point is. Now, of course, we're never doing this graphically. We're always going to be doing it mathematically. But knowing how these curves behave as you change different characteristics of the piping system is important to understanding what's going to happen to the flow rate and how much is it going to increase or decrease with various changes. Now, something else that we're interested in is how much power is the pump consuming. Remember, the pump is an energy input into the system, so we want to talk for a moment about how much power is that, or what is the rate at which energy is being put in. Well, you might recall from thermodynamics that for a 100% efficient pump, or an isentropic pump, we called it there, the work on a per unit mass basis is minus the integral of V dP. Well, in this course, we're looking only at incompressible fluids, so this V can come outside of our integral sign, and we integrate that, and we just get minus V, the specific volume, times P2 minus P1. Well, again, in this course, we don't really use specific volume, rather we use density, so we'll just replace that V with 1 over the density. And what we're more interested in, rather than the work per unit mass, which is what this is right now, we're interested in the rate at which work is being done on the fluid. So W dot of the pump. Well, W dot is the mass flow rate through the pump times the work per unit mass. So we take this quantity and multiply by mass flow rate, and we're only interested in the magnitude of this, so we're going to drop this negative sign. So we get density times Q times the work per unit mass. So notice I've written mass flow rate as density times volume flow rate. Okay? Now, when we bring this in here for our work per unit mass, this density and this density are going to cancel. So we do that, and we get that the rate at which energy is being put into the fluid is the volume flow rate times the pressure change. So this is a very important equation to know. So in SI units, that volume flow rate would be in cubic meters per second, and the pressure increase across the pump would be in pascals, and that would give a pump power, in watts. Now the only other thing that we need to do to this is remember, this is assuming that the pump is 100% efficient, when of course it never is. So we need to divide this by the efficiency of the pump. So this is the rate at which work is being done on the fluid, but we need to divide by the efficiency of the pump to get the rate at which we actually need to supply power to the pump. So if this efficiency is, say, 0.7, then of course that's going to increase this quantity and give us the amount that we actually need to put into the pump in order to produce that flow rate at that pressure increase. Now, like I said, when we get to the turbo machinery section of the course, we're going to be revisiting this equation quite a bit, and we're going to be learning how to calculate or predict the efficiency of various types of centrifugal pumps. Now, the last topic I want to look at in this particular video is what happens when we actually don't have a pump, but instead we have a gravity-driven flow. So we're starting off here with our working equation. So we have our delta P pump on the left-hand side and our entire system curve on the right-hand side. But for a gravity-driven flow, there is no pump, so I'm simply going to set the left-hand side of that equal to 0. So when we take a look at system curves for a gravity-driven flow, then they're going to look like this. The only way we could possibly have any flow through this is if the system curve is shifted down, so it intersects this delta P equals 0 axis. So that means that the fixed system pressure, these ones, are driving the flow. So if we have Z2 smaller than Z1, for instance, going downhill, then this is a gravity-driven flow, and we can have a system curve that intersects this axis. So if the system curve looks like this in a gravity-driven flow, then that will be the flow rate. Okay, and of course the same thing happens as we change the fixed system pressure. Maybe we move the exit down even further, then our flow rate will increase. But we can predict what that flow rate is going to be just by setting our delta P pump to 0 and solving for the flow rate that results in a delta P of 0. Okay? So the last thing I want to do is take a look at this little illustration here. So this is a gravity-driven flow, and I'm showing two possibilities. So we have an elevated reservoir up here, 1, and a reservoir down at a lower elevation, 2. And notice I've got my Z equals 0 there and Z pointing upwards. So two large open reservoirs, and they're connected by two different piping systems. So all of the physical characteristics of these two piping systems are identical. So exactly the same size of pipe, exactly the same roughness, exactly the same length of pipe, although it doesn't look like it at the end here, but the lengths of these pipes are exactly the same. Number and type of fittings are all exactly the same. So the sum of the minor loss coefficients and the frictional losses, everything in those two piping systems is identical in this illustration. The only difference in these two piping systems is one of them is connected by a submerged exit going into this reservoir, and the other one just has an open exit, but it's at the same elevation as the surface of this reservoir. So pipe 2B there's going to be water spewing out of this end. Okay? Now the question that I have is, which one of these pipes, 2A or 2B, will have a larger flow rate in it, and why? So if you want to pause the video and think about that for a moment and just come up with an answer on your own, then you can press play again and I'll discuss this. So welcome back. Hopefully you hit pause and thought about this a little bit. Well, if we think about the system curve for these two situations, notice that P1 minus P2 is 0 in both cases. Notice that Z1 minus Z2 is the same in both cases. So the driving force for this flow is exactly the same. The elevation change from point 1 to point 2A or point 1 to point 2B is exactly the same. Okay? Now, if we look at what is different about these two scenarios, there are two differences. In this particular case, which I've called 2A, the submerged inlet, we have one extra minor loss coefficient here associated with that sharp-edged exit. And that Km, if you remember what the minor loss coefficient for an exit is, it's equal to 1.0. So that minor loss coefficient is 1.0. For path 2B, there is no minor loss coefficient here. This is just a free jet exit. Okay? So that's one difference between the two. The other difference between the two is that the velocity at point 2B is not 0, whereas the velocity at point 2A is, because point 2A is on the surface of our reservoir, where for path A, we're writing Bernoulli's equation from the surface of that reservoir through the pipe to the surface of this reservoir. So V2 for path A is 0, whereas V2 for path B is not 0. It's whatever the flow rate and the area of that pipe says it's going to be, but certainly not 0. Well, notice that those two effects exactly cancel each other out. So in fact, the flow rate through these two pipes will be exactly the same. So if we look at our system curve for path 2B, we'll have a kinetic energy term here, V2B squared over 2. Okay, and that will not appear for path A. But for path A, we have an extra minor loss coefficient, and by no coincidence, the minor loss coefficient is 1. So that contributes to the system curve for this one in exactly the same way as this kinetic energy term. And physically, the reason that's happening is this minor loss coefficient is there to account for the fact that as this water enters this reservoir and mixes with this stationary fluid, all of that kinetic energy that it possessed there is lost. It's just dissipated into heat. So that means the minor loss coefficient has to be 1. Because remember the way minor losses are calculated. Delta P minor is equal to a minor loss coefficient times rho V squared over 2. Okay? So if this is exactly 1, it means the minor loss is equal to the kinetic energy at that point. Well, that's exactly what's happening at a sharp-edged entrance. All of the kinetic energy is being lost. So in fact, in this case, the flow rate through these two things would be exactly the same. Okay? So think about that for a moment. Go back and take a look at the system equation if you're having trouble with that. But I think you'll see that the flow rate at the end of the day is the same in these two cases. So thanks for watching. This is the last lecture video for this module in the course. Be sure to watch the example videos and follow through those. And the next module of the course, we're going to be looking at dimensional analysis. Thanks for watching.